ever just stopped and wondered how your phone's autocorrect kind of knows what you meant to type? Or how a search engine seems to understand the idea behind your question, not just the words? Well, today we're going to break down that exact journey. How we teach a computer to understand human language, not just as a bunch of letters, but as this huge, interconnected web of meanings. Okay, so let's just dive right into the heart of the problem with this question. I mean, to you and me, great and fantastic, they're synonyms, right? They have a similar positive vibe. But to a computer, on a really basic level, they're just two totally different strings of characters. And this visualizes the gap we have to bridge perfectly. See, our brains are wired for context. We just know that great and fantastic live in the same neighborhood of meaning. A computer, though, it sees them as completely separate things, as unrelated to each other as great is to, say, apple. So how on earth do you teach it that context? Well, the first hurdle is a big one. It's a fundamental problem in machine learning that has a really cool name: the curse of dimensionality, or, as we're calling it for our purposes, a curse of many words. Just think about it for a second. The English language has hundreds of thousands of words. If we try to treat every single word as its own unique feature, we create this massive, sprawling data space. And here's the problem. Most words are used very, very rarely. This makes our data sparse. It's mostly empty. And that makes it incredibly hard for an algorithm to find any reliable patterns. How can it learn that great is like fantastic if it's barely seen either word? So, if just counting up every single word is a total dead end, what's the alternative? Well, the big breakthrough actually came from the world of linguistics, not computer science. And it's this beautifully simple idea about, the company that words keep. This one sentence, right here, from a linguist named J.R. Firth back in 1957, it changed everything. This idea is called the distributional hypothesis, and it basically says you don't need a dictionary definition to understand a word's meaning. You just need to look at the other words that show up around it. So here's the absolute key takeaway. Meaning is defined by context. Words that tend to show up in similar contexts, well, they tend to have similar meanings. It's actually a super intuitive idea that, honestly, we all use every single day without even thinking about it. For instance, if I give you this phrase, bagels with, what word just immediately pops into your head? It's probably cream cheese, right? And you know that because you've seen the words bagels and cream cheese hanging out together countless times. That very association is a huge part of their meaning. And this is the exact principle that we can teach a computer. Okay, so the idea is cool, but how do we actually make a computer do this? Well, the very first attempt was, pretty literal. Let's just start counting a word's neighbors. The process itself is pretty straightforward. First, you pick your target word. Let's stick with bagel. Then you go through a huge amount of text, and every single time you find the word bagel, you look at the words right next to it, its little neighborhood. And then you just tally up all those neighboring words. And what you get is a list that looks something like this. It's a breakdown that shows, after scanning our text, bagel is most strongly associated with, surprise, surprise, cream and cheese. This list of neighbors and their counts is called a co-occurrence vector. It's basically a raw numerical profile of the word's context. But here's the catch. To do this for real, your vector needs a slot for every single word in the entire language. We're talking hundreds of thousands of dimensions. So we're right back at that curse of dimensionality. These vectors are gigantic and mostly filled with zeros, not very useful. So the next big idea was compression. We needed some way to take these giant, sparse vectors and just squish them down into something way smaller and more meaningful. We wanted to keep only the most important bits of information about that word's neighborhood. And the solution is this really powerful mathematical tool called singular value decomposition, or SVD. Now don't worry, we're not going to get lost in the math. What's important is what it does. It takes that giant matrix of all the word vectors, breaks it down, and identifies these hidden concepts or topics that connect all the words. And crucially, it ranks them by importance so we can keep the good stuff, the signal, and just toss out all the noise. And the result is pretty dramatic. We can take a vector with hundreds of thousands of dimensions and compress it down to a dense, really meaningful vector with just a few hundred dimensions, say around 200. We've basically created a compact numerical fingerprint for each word. The only problem?
this whole process was still incredibly slow and super expensive to compute.
And that leads us to the major breakthrough, the one that really unlocked this technology and made it usable for, well, everybody. It was a new approach that completely flipped the problem on its head. This new idea was called word-to-vec. So, instead of the old method, counting up all of a word's neighbors to define it, word-to-vec's goal was to get good at predicting a word's neighbors. It sounds like a subtle shift, but it's profound. This new prediction game was so much more efficient. It turned a problem that was basically impossible into something totally practical. And the vectors that this new method created, they were absolutely incredible. They didn't just know that great and fantastic were similar. They had somehow learned the deep relationships between words in a way that feels, well, almost magical.
Take a look at this. This is the most famous example. If you take the numerical vector for the word king, and you subtract the vector for man, and then you add the vector for woman, what do you think you get? I mean, the math is literally capturing the concept of royalty minus the concept of maleness, plus the concept of femaleness.
Boom! You get the vector for queen. This is astounding. It means the model didn't just memorize word definitions. It learned abstract concepts like gender and monarchy, all just from analyzing what company words keep. It's incredible. But as powerful and amazing as these models are, they are not perfect. And their flaws, well, they reveal something pretty deep and frankly a little unsettling about what it means to learn from human language. There's kind of a ghost in the machine. So, there are still some major challenges. For one, we don't actually know what each of those 200 dimensions in a vector means. They're not really interpretable to us humans. Second, a word like bank, a riverbank or a money bank, it gets just one single vector. But the most serious problem of all is that these models are a mirror. They reflect the text they were trained on, including all of our human prejudices. For example, research has shown pretty clearly that these models learn and sometimes even amplify the gender and racial stereotypes that are already present in the data. They learned, for instance, that the mathematical relationship between doctor and father is almost the same as the relationship between nurse and mother. It's a stark, numerical reflection of a societal bias, and it was learned directly from our own writing. And this leaves us with the most critical question of all, really. We've done it. We've succeeded in teaching machines to understand the meaning in our words by looking at their context. But if our language is filled with the context of our own biases, our own flaws, what does that mean for the future of AI we're building? And maybe more importantly, what's our responsibility in trying to fix it? Definitely something to think about.